Okay, everybody, let's get started. So now the formal inauguration is over, so now the fun begins, right? So all right, so we did have a little round of introduction. What I usually do is I usually start my courses by doing a little introduction. Everybody got the homework 0 yesterday. Is anybody here who is not part of the WhatsApp group? Everybody is good on WhatsApp? You're already added and stuff? Okay. So I have received, I think, already 10 or 11 submissions. Those of you who have not, please do that. There is a reason I collect that, and you will know that at the end of the session. And also, there is a question about your favorite song. Remember? There is a reason I also do that. So I'm a very, very big music fan. I listen to music all the time when I'm working, and it's very difficult to look for new songs or select songs. Every time I teach, I collect my students' best songs, make a playlist, and that plays for me. So I have like 10 or 11 playlists every semester I collect from my students. It can be any language. I literally listen to all songs. So if you want to talk music sometime, I'll be happy to do that. So it's not fair for me to ask for your introduction and not introduce myself, right? So that's the first thing I do always is Capital High School, Bhubaneswar. Anybody from Bhubaneswar, you should know that. The people don't go to Odia medium anymore, so you all may not know what this is. It used to be an Odia medium school. I think Umesh is also an Odia medium. Where is he? Disappeared right there. Okay. So then BJB College, then IIT Kanpur, Texas Tech, couple of years, University of Illinois. I stayed there for 8 years, and then I have been teaching mostly pavements, railroads, transportation, geotechnics. At Oklahoma State, I actually teach the Intro to Geotech class every semester, which is one of my favorite classes to teach, because as I said, those of you who are working in the field of transportation infrastructure or pavement or anything, trust me, no pavement engineer is going to have a solid foundation unless you know geotechnical engineering. It's an absolute must. So every famous geotechnical pavement engineer you can imagine is actually a geotech by background. You start from the Carl Monismiths, the Richard Barksdales, the Marshall Thompsons. Their foundation is all, and in the modern greats like the Iyad Masad, the Imad Al-Qadi and stuff like that, all of them are very, very strong foundation engineers. Okay. Then Umesh, do you want to say a little bit about yourself? This is your slide. No? Okay, I'll continue. Umesh has been a good friend. By the way, one more thing. There are some PhDs. I think Ottanu, where is it? Ottanu, somewhere sitting right there. He's a PhD, and some other people are PhDs. So I've been in the US for 20 years, right? So I am very much into first names. I will not call you Dr. Behera. I'm sorry, it is not out of disrespect. I will call you Ottanu. You can call me Deb too. That's fine. I'm a very informal person. So anyway, Umesh, he's been a good friend for several years now. He has been the primary person that has connected me to IIT Bhubaneswar. Tanmay is somewhere here, right there. Tanmay is actually a student that we are co-advising. It's been a lot of fun working with them. So he's the host faculty and stuff. So you do remember one thing about this class is, this is probably the only class you will attend where the instructor actually encourages you to use your cell phone. So get out your cell phones. Everybody has a smartphone, right? Does anybody still have a flip phone, old Nokia? No? Good. Smartphones. We need a smartphone. Let's do this QR code quickly. Okay. So this is a thing called Mentimeter, where we are going to monitor several things. Sometimes this thing creates issues. Okay. PhD scholars. How many are submitted? Others. This is the class composition, what we have right now. So go 10 masters. Where are the faculties? You don't have your cell phones? I know there are at least couple. Or maybe faculties are slow in using cell phones. Reasonable explanation, right? No? 23? Some people have not submitted it yet. How many do we have? I have to. I think there are more than 23 people in this room, aren't there? Some have not. Is it not working for some people? Okay, so that's the composition. Okay, a lot of master students. That's good. That's actually in a way good. I do have some fundamental stuff in here that we are going to cover, which at a master's level you'll find more useful. If you're a PhD or a postdoc, you may already remember this, may not remember this. We'll go through that quickly. Okay, and I said this already. You are going to submit this. It's mandatory. If I don't see somebody, I'll chase you down. So please submit this whenever you get a chance. Number 5, I was actually a little bit disappointed by some people saying that I don't have any unique experience. So I'm going to give an example, and then I will give you all the chance to modify your answers, those of you who have submitted. Okay. So I have a unique experience that I can guarantee you will not hear from anybody else in your entire life. That holds for every country. This holds for America, holds for India and everywhere. And I am the only person that you will ever know that was once bitten by a dolphin. So here goes the story. So I went to Florida. This is back, I think, to 2012 or something, with myself, my wife, my mother-in-law, and my brother-in-law. We went to Florida, and there is a program called Swim with the Dolphins. Okay, so what you do is you go in the middle of the ocean. This is like south, right? It's basically where the Atlantic and the Gulf of Mexico join and stuff. So you can actually swim, and there are a lot of dolphins, and people swim. And I love swimming in the open water. So the captain was keeping telling me that, why don't you swim, why don't you swim, why don't you swim? I said, no, these are wild animals, I should respect them, I should not swim with them and stuff. So he's like, no man, you paid all this money, you should go and swim and stuff. And I'm like, okay, we should probably do that. So then I went to the water, right? So what happened is, for about half an hour, there was a mother dolphin and a baby dolphin that were following the boats, and they were looking for food and stuff. And remember, I don't know what you know about dolphins. They are big, okay, and especially when in water, they're really big. Like I'm talking, the mother dolphin was about 9 feet long, and the baby was probably about 5.5, like probably my height, 5'8", 5'6", 5'7", something like that. So then I was swimming, and then all of a sudden, what happened? The baby dolphin just came to me. So that's my brother-in-law taking pictures. He didn't know it would become like a story. So that's the baby. Okay, you can see how much long it is. And then it just went down, and I was trying to swim, right? So it went down, and it grabbed my arm like this. And then I was in deep water. I said, I told the captain, I was near the boat. I told the captain, I said, hey, it's trying to bite me. I said, you'll be fine. I said, what the heck do you mean you'll be fine? I'm going to die in the middle of the ocean or something. So I pulled my hand, and it basically, this is the teeth and stuff. So it basically did a complete, like almost like a little saw bite or something like that. And then I tried, and then it went away, and it was trying to come back to me, and I literally punched it. I literally almost boxed it, and then it went out and stuff. So that's my unique experience. This is a picture I show everybody in every semester I teach classes and stuff, and I ask for it. So now you can go back and revise your submissions if you want. I'm sure people you have unique experiences. So yeah, that's why I say this. This helps people to remember each other. Okay, how are you going to do this class? We're going to start about 9:45 every day. We'll go till about 11:15. Then from 11:15 to 11:30, we'll have a short tea break. Then 11:30 to 1. And then 1 to 2, I think, is lunch. Is that correct? 1 to 2 is lunch. Okay. And then we'll do a hands-on exercise from 2 to 3:30 or something. And the whole idea here is, and the good news is there is so much students, so I don't feel bad pushing you guys to do things. What you should do is bring your laptops, and I will give you Today I'll give you a paper, you're going to read it, and it's something called statistics driven borehole location or soil sampling. Like for example, if you're given a 60-kilometer road to construct, and your boss or your budget says you have only 100 boreholes or soil explorations you can do, how do you do that? Where do you place them? Where are the 100? Is it always divided by the distance, or is it based on some prioritization? That's what we're going to do. So basically what you'll do is, today is the first class, so I didn't want to give it in advance. So today during the tutorial you're going to read the paper, most likely you will not finish it, we'll see, and then I want everybody to build a spreadsheet for a problem that I'm going to give you so that you know how to do this and stuff like that. Then as we move along, we'll do other things like, I have triaxial testing data. I'll give it to you, and then it's up to you. You can write a Visual Basics code, a Python code, a MATLAB code, or whatever you want to do to read the data and spit out whatever you want to do and stuff. So that's what the tutorial is going to be. So bring out your laptops and stuff, and we'll do that. So today we're going to talk about the design philosophy and historical development. Okay, so show of hands, how many of you have taken a pavement design class in your life? Okay, most of you. That's good. Okay, so we're going to talk about the historical development, how things started, what is the philosophy, how the philosophy has changed over time, and what's happening with respect to the modern designs and stuff. And then we're going to go into railroad and pavement substructure layers and their importance. And there are some of you have actually asked some interesting questions in your submissions, which was actually pretty nice, saying that, okay, what can we do this? What are the concepts? Why is our design state in certain condition in India versus other countries and stuff? So we'll address some of that and whatnot. And then we will try to end up with something called mechanistic empirical pavement design framework. Now, the good news is, and we'll get to that at the end of the day today, but the good news is if you look at a railroad structure and if you look at a pavement, it's actually not very different from each other. In a pavement, the tires are going directly on top of an asphalt or a concrete layer, whereas on a railroad, the train is going on a rail, the rail is going to what is known as cross ties or sleepers, and underneath that it's the same. Underneath that it's the same. As long as you just combine what is known as a beam theory, continuously supported beam or something, with a layered elastic formulation or something, that's what your railroad design is. So the good news is all the concepts we're going to talk hold for both the systems. So that's how, pretty much any railroad engineers you see, they also have a very good background in pavements and stuff, because the systems are very similar. It's all based on mechanics and stuff. And the tutorial today, we're going to do the statistically based soil exploration and compaction control approaches. So day 2, tomorrow we're going to do subgrade evaluation. Like you are going to have, you are an engineer, you need to go and construct a pavement, and then let's just say it's a realignment or a new alignment and whatnot, or I think there is some bullet trains coming and stuff like that, so you're going to do that. So what is subgrade evaluation? What are the methods? What do you recognize? What do you look for? What are the important properties and stuff like that? You probably know that pavements are the only infrastructure that are designed to fail, right? You don't design bridges to fail. That's going to be disaster. You don't design this building to fail and stuff. Pavements, you can design them to fail and stuff. So what is failure? What is the meaning of failure? What is the meaning of, what kind of properties do we look for? People who have a very strong geotech background, you probably know what is bearing capacity failure and stuff like that. I mean, is bearing capacity something that's important for pavements? Is that relevant? What are the properties that are relevant, right? What kind of stresses and strains do we talk about and stuff like that? So this is a good time for me to ask, and please don't hesitate. That's why we are here for 5 days, and I don't mind going over anything. How many of you are confident that you can tell me the difference between stiffness and modulus? Raise of hands. I saw a couple nodding their heads in a negative, and that's good. I appreciate that. That's what I want. How many of you can tell me the mechanics difference between stiffness and modulus? Okay, we'll get to that, because that's very important. That's very important for you to understand what's going on in pavements, in a layer, in whatever you're trying to determine. So how many of you have heard of the test called CBR, California Bearing Ratio? Most of you, right? Except for BTech students, I'm pretty sure. Yes. Okay. So what is it? Why do we use CBR? What is it giving us? How representative is it of what we are trying to measure? Is that a good measure? Is that a bad measure? If you are in the middle of nowhere in Africa and then you need to do some quick tests, is CBR a good thing for you? But what if you are a researcher and you're trying to advance the study and stuff? Do you still rely on CBR and stuff like that, right? Those are things that we're going to discuss tomorrow. Okay, laboratory and field methods, that's what this is. CBR, DCP, I think a lot of you have heard of it, dynamic cone penetrometer. We'll take a look at that. What does that give us? Why is that a useful tool for us and stuff? And then we're going to talk about laboratory and field methods, others, continued falling weight deflectometer. I'm sure a lot of you have heard of it. Some of you may not have. We'll take a look at that. There is something called lightweight deflectometer. So what is that? What is the concept? How does that work? What do we get out of it? There's something called geo gauge or a soil stiffness gauge. We'll take a look at that. And then tomorrow's tutorial will be CBR, DCP, and FWD data, where I will actually give you some data from real field experiments that I have run, and then I'm just going to have you interpret that and come up with some target numbers and stuff, saying that, okay, what do you understand about this soil? What is the average CBR? Because guess what? If you are making concrete, you know, okay, this is 4,000 psi concrete. If you are a geotechnical engineer, you have absolutely no idea what you're talking about, right? You're standing at one place, you do the measurements, 10 feet away, it can be completely different. So that's the reason. How many of you have heard, this is more of a question for the seniors, like PhD students and stuff. How many of you have heard the name M.R. Madhav in geotechnical engineering? Just one? Okay. Are you from Hyderabad? You know him? Okay. So M.R. Madhav was probably one of the most famous geotechnical engineers that India has produced. At least I would claim that's because I'm a big M.R. Madhav fan. He was a professor at IIT Kanpur. Then I think he's still teaching in some Hyderabad universities. Sometimes he does. He's one of the legends of the field, and he used to say this thing. This is when I was an undergrad, my very first geotech class, and his first class, he says, geotechnical engineering is a science, but its practice is an art. That basically really influenced me, and that's how I applied for a master's and stuff. So it's very, very intuitive. It's very you have to be an engineer to understand what's going on. You can't be a true scientist to do geotechnical engineering. You have to have some notion of, okay, this is approximation, this is good enough, this is what it's going to work. Day 3, we're going to go into shear strength, modulus, permanent deformation. I saw one question, I don't remember the name, but I found it very genuine. That person said that I am a little weak in geotechnical engineering concepts. Is that going to affect my understanding of the course? The answer is no, but the point is, if you still leave this class being very weak, then I have not done my job. And I like to do my job. So we're going to go over some of the things, like how many of you have ever seen, okay, let's go the other way. How many of you have run a triaxial test ever? Either repeated or static, it doesn't matter. That's a pretty fair number. How many of you have seen a triaxial test run? Most of you? Okay. So we're going to go really deep into triaxial testing. Why triaxial testing? What is triaxial? Okay, let's this is still in introduction. Who can tell me why is a triaxial testing cylindrical? Why is the sample cylindrical? Let me explain. What is triaxial? 3 axes, right? What is the 3 axes that we see? What's your name? Dhruv? Dhruv, what are the 3 axes in real world? Sit down, never get up, please. What are the 3 axes in Cartesian coordinate? X, Y, and Z. So this this, this, right? So it should be cubical, isn't it? Isn't it cubical? Why is triaxial testing cylindrical? Hold on, say it again. Yeah, radial. You are assuming all the radials are same, but why? Is it always? Can you guarantee that? No. That's cheating, right? It's like I'm not going to clean my house because I'm lazy, right? You need to fix your boundary condition. That's cheating. I mean, you are right, though. I mean, you are absolutely right that boundary conditions are easier to avoid in a cylindrical. But why? Why are we doing cylindrical? Same as boundary condition, same answer, but that's not the reason. Why do you do it? Again, it's assumption. I'm talking about triaxial. You call it triaxial. How many of you seen a drilling in function in operation? Have you seen a drill in operation? How does a drill move? In a circle. How are you coring the soil? In a circle. So what kind of sample are you going to get? That's the reason for cylindrical triaxial tests, because you're trying to replicate what's in the field, right? So we're going to go into all of these things. You never ever go and do a in the soil. You never do that. You do a drill. That's circular. That's cylindrical triaxial testing. That's the reason we do that. We'll get into a lot of that. We'll get into some more circles, some failure envelopes, some drained and undrained, and then we're going to go into some shear strength data. Day 4, probably by far my best topic of my entire life, because I spent my entire PhD doing this, which is known as repeated load behavior. Okay, what is repeated versus what is cyclic? What is cyclic? Regular intervals loading will occur, mostly correct. You're missing one little. Okay, let's go to math. You're all, we're in India, so we don't have an excuse to escape mathematics, right? We're supposed to be strong in mathematics. In America, I don't have that excuse. I cannot blame them a lot of times, because the students, they come, the high school system is very different there. But here I know, I studied here, right? So give me a example of a cyclic function. Sinusoidal, good. So how does a sinusoidal go? Sine 0 is, sine 90 is, sine 180 is, 270 is, minus 1. What does that mean? It has a positive component and it has a, so if I am applying a loading, what am I doing to the sample? Positive and? Go ahead, you said it right, positive and negative. How many times do you run a resilient modulus test and you push the sample and then pull it back? You never do. So anybody who tells them that a resilient modulus is a cyclic test, they have no idea what they're talking about. It's not a cyclic test. It's a repeated test, because it is positive, gap, positive, gap, positive. There is a history, right? Is that the same as mod of sine? Haversine. What is Haversine? No, it's not. Who remembers what is Haversine? Come on, mathematics. What is Versine? 1 minus cosine theta. What is Haversine? Half of Versine. 1 minus cosine theta divided by 2. So what is that? Sine square theta over 2. The 2 is gone. So sine square theta over 2, not theta anymore, it's a theta over 2. Why is that important? Somebody like Tanmay, he's actually building his own triaxial testing system. He needs to know all of this so that he's going to program the signal going into the system, right? It's not a sinusoidal wave. It has a rest period. Why is the rest period important? We're going to talk about all of that. So day 4 is going to be a lot of this. Day 5 is stress dependency. A lot of people will say, what is the resilient modulus of this soil layer? Right? The fun answer to that is you can get by as saying it depends. And you're still right, because resilient modulus is not a constant number. It depends on stress state. But we are still doing an E value in our designs, right? So what's the E? What does it represent? What stress state are you talking about? Is that a representative state? Is it at the top of the layer? Is it the bottom of the layer? Is it the middle of the layer? How does the stress bulb dissipate? Do we ever think about these kind of things? What's the difference between Young's modulus and resilient modulus? Everybody has seen Young's modulus, right? Vishwabandita, you have seen Young's modulus already, correct? What year are you in? Third year. So you've probably done mechanics already. So what is Young's modulus? Stress over strain, boom, right? Linear, right? What's resilient modulus? Is that the same? Is the resilient modulus an elastic modulus? We'll get to that. The answer is yes, but we'll get to that. Okay? Then we're going to do a little. Does everybody have a Windows based computer here? Except for me, I have a Mac, but that's okay. Does everybody have a Windows based computer? Yes, okay. So I'll give you this software called ILLIPAVE. It's free, so I'm allowed to distribute this. So this is finite element based pavement analysis program, and we're going to do some analysis to see how the stresses and strains are changing and stuff. At the very end, we're going to talk about anisotropic behavior. You said about the lateral stresses are the same. Is it actually the same? How does an aggregate layer or how does a soil layer behave when you compact it? Is it actually isotropic? Is it anisotropic? Is it truly anisotropic? If it is truly anisotropic, it should be this, this, and this, 3 different values. Is that how it works? Right? Are there any reasonable assumptions that we should be able to make and stuff like that? Any questions? And that should be day 5 for us, and then that should give you a good enough foundation to and I'll introduce, of course, resilient modulus models. You have heard of something called K theta model, universal model, MEPDG model. We're going to talk about what is MEPDG, why the heck it is the way it is, and stuff like that. All of that stuff. Okay? Any questions before we go about the course structure or anything that I missed that you would like to see? It's a live curriculum. I can change anytime. It's not fixed. All right. So that's introduction. Now let's jump in. Okay, this course will assume in-depth understanding of basic geotechnical concepts and mechanics, but again, we're going to cover whatever I see is not. And please listen, you have spent the time to come and spend five days here, so please don't be shy. If you don't know anything, raise your hands, right? The smart person asks questions, right? The people who underestimate others, who ask questions, are the real dumb ones, right? We're going to do basic understanding of pavement engineering. What are critical pavement responses? Why is that important? What is the difference between response and performance? What is mechanistic empirical? What is empirical? What is mechanistic? Why are they different? What are the advantages of each versus the other and stuff like that? If you're not familiar with some of them, talk to me, spend sufficient time. I will give you enough materials. Get out your cell phones. It's the same code, by the way, I think if I'm not wrong. Wait, you can actually stay there and I should be able to start this. Start Menti. What happened? Why is it doing that? That's not fair. Oh, I see. Yeah, there it is. Okay. What do you see on your slides, on your Menti thing? Is it the first question still? Okay, yeah, that's what it's saying, right? Hold on. I don't know why it is doing this. Let me see one thing. Slab display. Okay, now it should do that. Do you see a screen now? Okay. How well do you remember the following geotechnical engineering concepts? 10 is very confident. You need it again? I thought it should refresh. Okay, let's try that. Or do I, is it catching? Okay. These are average scores, by the way. '20, 21. Last time I think I had 23, 22, 23, 24, 26, 7, 8. Okay, this is interesting. I didn't expect this to be higher than that. That's okay. We'll see that. Compaction is not something that we will go very deep into. This one, but we will touch it and see what's going on, and then we will spend a lot of time on shear strength and repeated load. So you should be able to catch up on whatever is lacking and stuff. Okay. Okay, let's do this. Historical. So first of all, the slides use this in course. It's been compiled from a lot of courses I have taken, presentations I have made, colleagues I have worked with, professors I have had. So it's a lot of their credit. I have just reorganized some information. Some slides I just use directly. So I'm just the messenger. I always like to say this because credit needs to be given to people who deserve it. Okay. So what are the learning objectives after this end of Umesh? We don't need to break for tea again, right? So we can go all the way till lunch. We can go all the way till lunch. Okay, that's almost 2 hours. Okay, we'll see how that goes. Historical evolution of pavement design methods. Important role that Ashto-Roth test played in the history of pavement design. Recognize the difference between design methods versus analysis and performance prediction methods, right? What is a design method? Design method is where you provide your inputs, and then it will give you a design. It will give you your steel girder should be this size. Your concrete slab should be this thick or something. Is that what you do in pavements? There are some methods that kind of do that, but some methods you do something else. And what that is called analysis and performance prediction, right? So what is the meaning of that? What is the difference between response and performance and stuff? So we will go into all of that. Okay. So everybody said that you have taken some form of pavement design or something, right? So 1950s, it was mostly based on experience, okay? And pavement design was actually done by geotechnical engineers, okay? And you will be surprised that in most state departments of transportation in the US, even today, pavement design falls under the geotechnical division. Okay, pavement design, I'm not talking about materials. Materials is different, right? When you are talking about the mixed designs, the viscoelastic, it's not in practice. Viscoelasticity is not in practice, but the mostly mixed designs, the balanced mixed design. Some of you who are working in asphalt probably know that. Performance engineered mixes, which is what in concrete and stuff. So that's different. That's materials, right? But pavement design, when you are designing a pavement structure to withstand loading and stuff, it always falls under, mostly falls under the geotechnical division. And the reason is that they go very hand in hand. The soil exploration, soil properties, unbound aggregates, unbound materials, compaction quality control, all of that goes very, very much into hand in hand. Then question is, 1960s, they started doing what is known as development of empirical methods, right? What is empirical? Anybody? Based on experience, right? When it comes to engineering design, sometimes, I mean, based on experience is still correct, but sometimes it is based on past data, right, which is also experience. I mean, it falls under experience, but it's based on past data, based on observed behavior, based on what has worked, right, versus then. So people started doing empirical methods. They're like, okay, if you have a soil that is, you know, a low plasticity clay or something, just throw in 12 inches of aggregate on top of it, pave with a, you know, 2 inches of asphalt, you're going to be good for a local road or something, right? That's just very, very standard experience based design and stuff. Then people realized that, okay, we are doing empirical testing or empirical designs, and those empirical assumptions are based on our observation, but how many places can we go and observe, right? So, and what are these factors, what are the important factors that are governing my material behavior or structure behavior, right? So let's just talk about things like what factors affect pavement behavior. Akshay, right? Is it Akshay? What are the factors? What you are a pavement designer. I'm telling you design a pavement. What are the inputs you are going to ask me for? Inputs. Say again. Material property. Okay. Yes. That's elastic modulus. That's material property. Okay. What else? No, thickness is you are going to give me the thickness. What other factors? What are the inputs? What are your what information do you need? Traffic. I heard climate. So material, traffic, climate. Mostly all three of them, right? So now we are talking empirical, right? So let's talk about empirical. How many places can you go and observe? What works in Odisha, Bhubaneswar, Odisha, is that going to work in Jammu and Kashmir? Is that going to work in I think even in Telangana and Andhra Pradesh and stuff? No, because the soils are different, right? So empirical is, there is a very, very big, I should not say myth, there is a very, very big popular belief that empirical is always bad, okay? I don't believe in that, because empirical, as long as we are dealing with the data for which the empirical method was developed, it can actually work very well for you. If you really know your motorcycle, let's just say you know your motorcycle like inside out, right? you know that, okay, if I see that this is what's happening, I know I have this many mileage left, I can go, because you know your motorcycle. You don't need mathematics to calculate that. You don't need a mechanic to tell you that. You know your stuff, right? So as long as you are not extrapolating beyond what you observed, as long as you are staying the same material, same traffic, same climate, empirical may just be fine, right? The problem arose when people started taking one empirical method that was developed in Ottawa, Illinois. We'll talk about that, and it was applied all over the world. That's the problem. The problem is not that the method. Yes, it is not 100% based in science, but guess what? Not always you may need that, right? So ultimately, you have to do something that works, right? So then in the 1980s, you have initial mechanistic empirical methods. Okay, what is mechanistic? Follows the principle of mechanics, right? Follows mechanical equations. Good, that's good. What's the why can't we just have a purely mechanistic method? Why? You're right, but why? Okay, let's step back. Let's step back. I'm mixing slides here. This is kind of after like just before lunch stop, but that's okay. We're going all the way till lunch. I'm not. I can mix. What is response versus what is performance? Anybody? Let's go one step at a time. I have a wooden table here. I just came and put a very big load, maybe repeated or maybe got into an UTM, and I've started applying load on here. What is response? Stress, okay, somebody said stress. I think if somebody said, did somebody say strength? Strain, yeah, not strength, strain, good. So stress, strain, we're missing one thing, deformation or deflection, right? That's called response, right? What's your name? Do you drive? Do you ride a bicycle, motorcycle or something? Okay, Himalaya. Okay, so Himalaya is now going on a road tomorrow from here to Bhubaneswar. And he is driving on a road and he doesn't feel happy about it. So he calls Tanmay saying that, hey, you are working here, what is the wrong with this road? And Tanmay is like, this road has a micro strain of 226 or something. As a driver, does he care? Does a driver care about what is the stress or a strain or something? What does the driver care about? What do you care about, Himalaya, when you're driving on a road? Smoothness, very good. What else? Say more. Safety. I don't. Safety can mean two things. Explain a little bit more. Comfort is smoothness. Do you really care about rigidity? Unless you're talking about deflection. That's again smoothness. You said safety, right? Ah, no more. What's that? That's again smoothness. Close. You're all getting close. There is one thing that misses in all of our predictions, which is what? What do you do when it rains, Himalaya? When you're riding? You try to slow down or something, right? But why? Because you lose what? Surface friction, right? So ride quality and surface friction are the two functional things that you really care about, right? As riders, you don't care about stress, strain, deflection. That's the nerd's job, right? You all are nerds here, that's okay, but that's your job. But when you put on your driver hat, you don't care about those, right? So that, my friends, is performance, right? What else do you care about? You said something about ride quality. What affects ride quality? What's your name? Chanchal. Tell me what affects ride quality? No, that's what you are governing. What is the road giving you? What aspects of the road affect your ride quality? Roughness, okay, one. Wear and, okay, I mean, yes, but you're not using terms, but that's okay. What do you see on a road? There you go, potholes. One, what more? What others? Now let's think around lines of potholes. What are the other things? Cracks, transverse cracks, longitudinal cracks. That's what distress is, correct? Right? So now we are talking transverse cracks, longitudinal cracks, rutting, potholes. These are called performance. Right? Another aspect which gets ignored sometimes is the surface friction as well, because we don't have really good models to predict that. That's mostly the reason that happens, right? So we have response, we have performance. A mechanistic approach gives you what, Atanu? The response, right? We are, any day, all these master students, these PhD students can take a pen and a paper. They can give me really complicated equations to say that your horizontal strain is this much, your vertical stress is this much, your principal, your what's this called? Von Mises stresses are, the finite element people and stuff like that. But then what? Right? How does that translate to what you just built between Bhubaneswar and Cuttack? Right? You have cracks, you have rutting, you have cracks in two different directions and stuff like that. Performance. You need to link the two somehow. Right? Somehow all the students running your lab tests and doing these beam testing and measuring the flexural strain and stuff like that, they have to be able to say this flexural strain is related to this much alligator cracking when my loading is this much and stuff like that, right? That's the link. Anybody knows what's the link is called? Anybody? PhDs mostly? What's the link between response and performance? They have a name. Transfer functions. Prediction models, yes, correct. Transfer functions. I'm going to give you a reading assignment today by one of my professors, Professor Marshall Thompson. I wanted to introduce this first before giving this. He clearly says transfer functions are the weak links in a mechanistic empirical payment design framework. Because guess what? We are really good at mathematics. We can calculate stresses and strains any day. We can do finite element modeling. We can do all sorts of advanced viscoelasticity, blah, 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 all of that. The problem is how do you link that into that, right? So that's what mechanistic empirical payment design is. The 2000s completely focused on implementation of MEPDG, okay, all the way till now. There are still a lot of states, including the state where I am, which is Oklahoma, where implementation has not been very successful, and there is a reason for that, and we'll talk about those, because the transfer functions is what really gets you down. How many of you have heard of the Asho-Roth test? Yes? Okay. So the Asho-Roth test was actually something that happened in 1958 to 1960 in Illinois. But before we go there, here's a little history. You will have this reading there. So early bituminous pavements, there is tar macadams, sheet asphalt, butyl thick asphalt concrete. There is empirical design methods. Then they have some road tests. Then happened the most important event, testing event in the history of payment design, which is called Asho-Roth test. Okay, By the way, those of you, again, undergrads and junior master students, if you don't know, ASHO doesn't exist today. It's called ASHTO. Okay? It used to be called American Association of State Highway Officials. Now it is called State Highway and Transportation Officials. So there is something called, so it's the road test is not called ASHTO road test, it's ASHO road test, because ASHTO did not exist back then. But now it is ASHTO. Okay? So what they did is they went to Ottawa, Illinois, which is north of Chicago and stuff like that, northwest of Chicago, and they built this test section, and it was a 2-year-long effort, and they had funding from many agencies, some automobile manufacturers, some petroleum industry folks. They're like, okay, we really need to understand what's going on with road behavior and stuff. And then they constructed 6 loops, several test sections, and then several bridges as well. But the fun part of that experiment was bridges were like this tall. They were not like regular bridges that you have to build an embankment to go into or something. There is a fill and stuff. It is all at the same elevation, and the bridges were like little this tall and stuff. So they had some bridge design stuff happening as well. And they had real trucks. The military, the army provided trucks for them, and then they ran it for 2 years. And they collected a heck load of data related to how the pavements were behaving for different sections, different material properties, different thicknesses, different level of loading, blah, 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 all of that. And based on that, there was a lot of analysis, there is a definition of serviceability that they came up with and whatnot, and then they defined how the sections behaved. That became the foundation for pretty much all the pavement design methods moving forward, pretty much until the early 2000s, mid 2000s. In fact, still several states, even in the US, use a version of the ASHTO test, which is ASHTO 1993 or something. You probably have heard of this thing called structural numbers and stuff like that, which that's all coming from ASHTO road test, right? And then you have ASHTO design 72, 76, then 93. After 93, that is probably kind of when people started talking about, more mechanistic things and stuff. And then because they realized that the problem is the ASHTO road test had all the soils were in Illinois, so it was like a low plastic silt kind of a soil and whatnot. It's not very relevant to everywhere in the country or in the world. The trucks that they used, they were running for 2 years, and still the maximum, is everybody familiar with the concept of ESL, equivalent single axle loads and stuff? You probably have heard that. If not, please let me know. ESLs, they have about, I think, close to 10 million ESLs, and that's it. And guess what? If you go to a very busy highway, you can hit 10 million in 5 years easily, right? So the question is, how can we still keep relying on the ASHTO road test data? So this is all on the concrete side of things. So by the way, over the next 5 days, folks, you will realize that most of my examples come from flexible pavements, because that's what I work on. But the good news is transportation geotechniques applies to both. But the saving grace for concrete pavement design, folks, is that the slab carries so much of the load that you kind of have a little bit of tolerance. You kind of can get away with some poor engineering of the soils and stuff, not for flexible pavements, right? So this is 1894 was the first concrete pavement in Ohio, and then they started doing a lot of ASHTO guidelines. They had the Bates test roads. This is a history of the concrete pavements in the US and stuff. And just for information purposes. Now let's talk about, oh my God, really, dude, I made that. This is what happens. Where is mine? It auto-corrected somehow. So the test site was at Ottawa, Illinois. 1956 where construction happened. 6 loops and a tangent, half concrete, half asphalt, 836 test sections, 16 short span bridges, and it was inaugurated in 1958 and it ran until 1960, and a lot of testing data was collected and stuff like that. The objective of that, and this is what happens, it's a very good example of something being done and then people not following up on that the way they were supposed to be, and then getting wrong results. The objective of the ASHO road test was that every state DOT was supposed to take that and model some kind of an empirical method in their own state, collect some data in their own state, and then implement it. The point is, when you are working for the government or when you are in the public departments and stuff, you are always constrained by money. You don't have money, right? So people didn't have the money to build their own test strips and stuff like that. So it basically ended up direct usage of the results from Illinois. And of course there is a problem, right? Of course it's not going to work very well. Pretty much Minnesota was, I think, the only state that actually did build a section and stuff like that. So we're going to talk about why am I going over all of this, is we're going to see where transportation geotechniques come into the picture in the big frame of different pavement design approaches and stuff like that, right? So empirical design, simple to apply, but what to do with the new materials, construction procedures, traffic characteristics and stuff like that. So let's